All right, so we're moving on to the second fundamental theorem. How do we know when we're going to apply the second fundamental theorem?
We got the exponents in there. T.
Okay, you've got t in the function. Not a bad observation. Most notably, though, you've got this d dx in front. That's how we know we're going to apply the second fundamental theorem. So we see that d dx in front. What that tells us to do, it tells us to take this top expression on our interval, replace any t's that we see within the function we're applying this integral to. As we plug in, I'll bring it down here, we've got the square root of, it'd be 2x squared minus 1, replacing t, plus 1. After we plug in that expression, we take the derivative of the expression. So derivative of 2x squared minus 1 would just be 4x. We multiply that on. Then we subtract. Take this first expression on the interval of x, plug that in for any t's that we see in the function. And the square root of x plus 1. Take the derivative of x, which is 1, attach that onto the end. And the rule was on these problems, simplify within reason. I'd say it's pretty reasonable in this first expression here to cancel out the 1's. And if we do that, we would have the square root of 2x squared. In fact, anytime you've got these roots, whatever follows the rules that we're multiplying, this 4x, we bring that to the front. All along, we're subtracting this second expression, which is just the square root of x plus 1, since we're multiplying to 1. And I would say that that's simplified within reason. You know, number 8 is the same kind of problem because you got this d dx in front again. So applying the second fundamental theorem, start with the 3x squared. Plug into the function for any t's that you see. You've got the 1t in the denominator, so you get 1 over square root of 1 plus t gets replaced with 3x squared. Now take the derivative of the 3x squared, attach that on. We multiply that on. We're multiplying a 6x on. We're subtracting. Now I'm going to plug in this sine of x. Got 1 over square root of 1 plus, replace t with sine of x. At which point we multiply onto this one the derivative of the sine of x, which is cosine of x. If we clean up this problem at all, once again simplifying within reason, since we're multiplying fractions here, we could take these derivatives that we attached and just bump them up to the top, make it 6x over square root of 1 plus 3x squared minus cosine of x all over square root of 1 plus sine of x. All right, so this kind of problem, we'll have to apply the second fundamental theorem as well. We won't have to apply it initially, though, when we find what f of 3 is. Because if you recall, to find f of 3, all we're doing is we're taking 3 here, we're replacing x in the original function. The only x we see is up here. So since that's going to create a definite integral that has an interval that doesn't change from 3 to 3. I spell out the rest of this here. Since that interval does not change, remember all of this just goes to 0 because the area beneath that curve on that interval would be 0. The tricky part is this minus 5. Remember, I'm just plugging in 3 for x, so really this minus 5 I'd be moving over, so I'd be adding it over to the other side. So if all of this becomes 0, just adding on 5, f of 3, It's going to be 5. The next step on these problems is figuring out the derivative of the original function with 3 inserted. So to do that, we have to take the derivative of the original function. So that's usually where underneath here I find out what f prime of x is going to be. Understanding that I'm applying the derivative to the original function up here on the interval 3 to x. Remember, I've slid that 5 over. I've added that over to the other side. Having done enough of these problems, we recognize that if we're going to take the derivative here, we've got the d dx in front. We're only applying the second fundamental theorem. If there's an x on top, well, we know that x is going to go in the place of this t, so it's going to be the square root of x squared minus 8. Then the derivative of that x becomes 1, so we could attach a 1. And then we subtract, understanding we're plugging in this 3, right? 3 goes in the place of t, derivative of which for that 3 is 0. The rest of this stuff just kind of cancels out. So what I have right here ends up being the first derivative. And if you want to keep things simple and just say, all right, x goes in the place of t, and that's all I need to do here because, hey, this is a constant down here and this is just an x, then that's fine. Just do that. Once you have your derivative, take 3 now, because remember, this is what we're trying to evaluate right here. Plug in 3 for x. If you plug in 3 for x, you got 3 squared 9 minus 8, so that's 1, square root of which is just going to be a 1. So f prime of 3 is 1. The last piece on these problems is usually some problem that involves a second derivative. It would make sense here to explore the second derivative when 3 is plugged in. So if we're going to figure out what that is, we should transfer over what the first derivative was. First derivative, again, was the square root of x squared minus 8. We want to find the second derivative. We're going to take the derivative of the first. So we're taking the derivative of x squared minus 8 raised to the 1/2. As we take that derivative, we're using a chain rule, so we bring down the 1/2. Quantity of x squared minus 8 stays the same inside. Subtract 1 away from the power, and then attach the derivative of the inside. Since we have to evaluate this, we'll clean up this function. To simplify, we're setting up a new fraction. We've got a denominator of 2 in the basement. We've got this negative exponent that we drop down, which we can now make just a nice clean root of x squared minus 8, because the power would be a positive 1/2. And in our numerator, we've just got the leftovers, so leftovers would be a 1 times a 2x. If you want to simplify that a little bit more, you could by canceling out the 2's. But basically, this is my second derivative. Plugging into the second derivative 3. Let's see, 3 goes in for the x's, so I'm going to have 3 over 1 again, right? 3 goes in, 3 comes out. Recall in these types of problems, because you do end up with these roots quite a bit, that's a popular kind of problem to have with these, that you may have some square roots in your answer. That is possible.